Um, Thank you very much, Marek. Welcome, everybody. Good afternoon. First, I would like to thank Marek for organizing this wonderful trip and visit. And Prague is an amazing city. And I would also like to thank Professor Sturridge for actually having sent Marek to our lab to spend time with us and creating this bridge between Stanford and the university here in Prague, the Technical University. So today what I want to talk about is one specific aspect of the research that goes on in my lab. Overall, we are really looking at how to design future electricity grids that are decarbonized, that are climate resilient and equitable, and in particular, they can support the emerging demands due to electrification, for example, electric vehicles, moving heating into electricity in this context. That's the research we do in a broader context. But today specifically, I want to talk about how do we use AI to understand how to better plan the deployments of certain technologies in this grid, particularly technologies that are deployed at the grid edge on, like solar, PVs on your rooftop, batteries, and so on. And I'll show you what's the big challenge there, how AI can really help, and what are some of the observations and outcomes you've had out of the research. First, I just wanted to say, well, what are the future electricity system goals? So we know today that because of climate change, we have reached some level of commitments to decarbonize our economy. And what's been realized is that a key aspect of this transition to a carbon-free economy is a strategy called electrify and decarbonize. It means you move a lot of sources of demand, like your building demands, transportation demands, into electricity, and then you decarbonize the electricity infrastructure. That's the idea. The buildings and transportation and so on is roughly 30-some% of carbon. Grid is another 30-some percent. So just this strategy would get out 60% of your carbon if you're able to do this. So that is decarbonization. But we are also facing additional challenges. For example, we face climate resiliency. Climate change is already happening. And if you look in California, there's several major wildfires that have either been started by the grid or the grid has been subject to them, really challenging the way we need to operate the grid to ensure power is delivered to everybody. And at the same time, we are trying to tackle this issue of equity. What do we mean by equity? This is a question I had when the federal government in the US launched various incentive programs, and they said that they have to be distributed equitably. That means we want to look at the characteristics of communities, income, access, etc., social status, how much pollution are they subject to, and various other criteria at community level, and take that into account as you design the solutions so that the benefits are enjoyed by everyone. Now, I've been working in energy systems and energy systems design for quite a while, and I can tell you, we barely know how to design in the ideal computer world, we're not even talking about real world, a decarbonized grid. Now, if you add climate resiliency and equity, we have no idea what we're doing right now. Literally, we don't know what to do. And we don't know how to necessarily measure it. We don't know how to incorporate these measurements into design. And then how do I take these three at the same time into account in these decisions for design and then later for operations? But you have to remember, these three criteria were not used in the grid. What was the most important criteria for which we engineered the power grid? It's really reliability. That means anytime you click that switch for turning on the lights, 99.99% of the time, literally 99.99% of the time, it will turn on the lights magically, and you're never worried about it. So how do I incorporate these three criteria while ensuring the grid remains reliable? That's the real challenge, and how to do it economically. And it involves technology, it involves economics, it involves policy and people. So what excites me about research in this area is no matter your background, you can really jump in and contribute. Now let me show you one specific issue we started looking into to try to address this. So as I mentioned, our infrastructure system is undergoing this dramatic change. For example, in the grid, we are adding wind power, we are adding solar systems in a distributed way. We have some climate events that may be hitting it, and you can see some pictures there of all that. And one of the key thing is that when you have all these changes happening at the same time, what are the challenges that emerge? First of all, when you add renewables, there are questions such as, where is the adoption happening? In the old world of purely centralized energy, because renewables can be quite distributed. It can be at the level of a single home, of a community, of a city, of the utility, which is the grid scale. And there's this question, how is this adoption happening? Where it's happening across space and time? How do the different policies and incentives actually impact the adoption of these technologies? And how to promote equitable adoption. And you can see here, just in this picture, the colors are changing very fast. That's the number of policies to ensure renewable adoption that was introduced in the United States. And they vary state by state. They vary sometimes at the community level. There is federal rules. They are introduced at different points in time. So there's a lack of clarity of what is the impact that investment that I'm making through money, tax money, is having. And how should I understand this? That's one huge issue. The second issue with renewables is that really when you think about the grid today, pre-renewables, you have these very controllable sources of power. I go to a power plant and I tell it to dial in and produce a certain amount of power, and it will sustain that amount super reliably, very controllably. And then if a few people turn on their lights, or everybody's watching the World Cup final, everybody turns on the TV, I just tell those power plants to increase their production to a set predicted amount, and they will all follow that, and I will have perfect balancing. Well, with renewables, the production depends on weather, it depends on the capacity of the technology to convert wind or solar into power, and therefore there's a lot more variability and unpredictability. How do we balance the demand and supply in that case? So that becomes a real issue. And one of the keys that you have to start thinking about is maybe there's some opportunity to not just look at the supply follows the demand, which is our current paradigm, and start thinking about smart demand. If I send price signals, or if I control the way my electric vehicles are charging, or if I am giving different types of incentives, people can change the way their demand is happening in real time. The next challenge is, of course, the challenge of extreme weather events. And the big issue with extreme weather events, in my opinion, is that it's not a local issue. So if I say, for example, forest fires in California, they are spatially distributed through a good chunk of the state, and they dramatically impact the grid in all those places at the same time. As an engineer, our method of designing and operating grid today is called N-1 reliable. What does that mean? At any time, I can have any one piece of equipment, a generator, a transmission line, completely fail, and there will be no power disruptions at all. It's pretty amazing. We actually have advanced that to N-2. This is a huge issue computationally, but also in feasible execution of how to make that happen. But N-1, N-2 is not applicable if I have a forest fire that now affects a transmission line, a generator at the same time in one location, and then the fire is spreading. There might be another source of fire somewhere else, and it's a very warm day, so everybody's turning on their air conditioning. So this is like n minus 100, and that's totally not possible to deal with in this methodology. I just wanted to bring this up to show you it's super challenging. There's a lot of exciting things to solve, and you can start seeing, well, there is a place for AI in all of this because there's lack of information, a lot of uncertainty, and very challenging optimization problems to address. But one very first problem we faced when trying to understand this distributed energy resources and where they were going is that there isn't a lot of data out there, openly available, that tells us who adopted solar, who deployed distributed wind or storage, and where is it happening, and when. So if I knew that, I can actually start answering questions such as, how does the dynamics of renewable energy generation can vary across different places? I can also answer questions of, well, I know there's a lot of people who adopted rooftop solar in this area, so maybe even if the grid fails, they're somewhat resilient to climate, right? And I can take that into account when I'm operating the grid. So for doing that calculation, I need to know the solar panels are there. I also need to know where the distribution grid is. So all of this information is not publicly available information. In fact, the traditional ways to actually collect this information involve several things. One, voluntary data contribution. So for example, there are voluntary registries like in Germany that you can go and declare you did install a solar panel, etc. Crowdsourcing. So if you go into OpenStreetMaps, some people, for God knows what reason, they decided to document in there they saw a transformer. That's pretty amazing. Why would but it's an open, crowdsourced information. Other than that, a lot of the information is sitting in silos such as the utility, regulatory agencies, technology providers, etc. And you're not able to really get all that information to start understanding things. In the US, because of these issues, the federal government created a program called Tracking the Solar. It used to be an $8 million a year program. Now it's something like $3 or $4 million every year for since 2009. So it's quite a long run, where what they're trying to do is they write to the state level regulatory agencies. This program is run by our national lab. And they get the documents of people who applied for various incentives to track the installation of these technologies. As you can see, there's various limitations. One, you most likely only get, for sure, those installs that were that are utilizing incentives, which right now in the US, nearly everyone. Second, it really depends on the quality of the document, of it being present. In 2017, we looked at this question, and at that time, they were 2 years behind on all the installations and so on. And in fact, we had gone to a utility who actually supposedly knows everybody who has a smart meter and talked to their planning group. And they told us, well, we would love to know where all the solar is in a super easy to access way. I asked, but why don't you go and get all the documents of the customers who signed up with you? They have to declare they have solar. Well, we have some regulatory rulings that don't allow us to necessarily directly access the information, and the other guys don't have it in a database. They don't have the lat long. It's all very complicated, and we left it at that. And in that meeting, I had a student with me, a PhD student, who was just starting out. At the time, he was a master's student, Jichang Wang. He went, it was May, we went back home, we went to do other projects. I completely forgot about this. 3 months later, or 4 months later, I received a call on a weekend. And normally nobody from the lab calls me on the weekend on the phone. And he said, Ram, help me, I'm very nervous. I said, what happened? Can you pay I think it was $38,000 bill. I said, what happened? He said, well, you know, me and this other student, we decided to use deep learning and satellite imagery to map where the solar is. And I signed up on my credit card on Amazon Cloud and started doing this project. And this is the bill. And it took us about 8 months to figure out how to transfer that amount of money to his credit card and pay. But what was amazing to me, within 3-4 months, 2 students were able to generate a method using a lot of existing classifiers and retraining them and so on that actually produced granular information. So that was really kind of what we're talking about when we say AI-enabled infrastructure informatics. We take raw data of different types. Satellite imagery is one. High-resolution aerial imagery that's available in Google Maps or Airbus provides it, etc. You can see some examples there of a solar panel. You can see the wind turbine, the presence of it, but actually what we found in our research, you can use the shadow that you're seeing there, and you can estimate the height of the wind turbine. You can use Google Street Views and actually map distribution lines. You can use building permits and even find where stuff that was installed inside your home is actually installed. And so we created various methods to harness all of this raw data and then create various layers that then produced analysis. And we really took a socio-technical lens, intersecting the grid infrastructure with climate risk and human factors. And this is kind of our research. It was into 2 buckets, and that's what I'm going to enter into details next. So I'm just going to go a little quicker here on the methods, but one, you're welcome to try them yourself because everything is on GitHub, and you can download and try it. And I want to talk about 2 separate areas. One is about the solar panels themselves. The other is about the distribution grid, and just show you how much information you can generate. And actually, this data is now used by other researchers, by various companies that sell solar panels, like Tesla, Sunrun, etc. And by, to our surprise, by some of the state regulators, which actually found it very, very useful. So our very first project was Deep Solar, and came from this realization that you can actually see the solar panel on all of the Google Maps maps from the top. And the question for making Deep Solar happen was 3 things. One, we wanted to have very accurate detection. Second, we wanted to measure the size of the panel. And third, all of this has to happen in kind of a feasible time, because the goal was to map the whole US. And so the method we created in Deep Solar gives us a recall of 90% and a precision of 93%. And really kind of the trick to doing this was that we took an existing model trained for regular images provided by Google, and we trained it to detect solars in whole tiles of images. That was the main advance that we realized. You don't have to do pixel level detection. You can detect objects by just saying the object is present on those images. And then by having enough training data, it picks up that you're trying to detect a panel. Then the other thing we realized is in some middle layers, you can actually pull information from the neural network and find the size. Recently, I even tried this just directly on GPT, and it can do it. It does a pretty good job if you give a few examples. The only issue is it's very slow. It would take us, we calculated something like 30 years to do the US. With this and our simplifications in running the neural net, it took us like a month for the whole United States. Okay, so the next question was, I need to detect the time at which the panel is installed. And here's the challenge. The challenge is that you could see the resolution of the satellite imagery was low in older years. But what was the key insight here is that if I start from a location that has a panel and I look backwards, I can kind of see that in 2016, despite it being low resolution, there seems to be the panel there, and then 2015, 2014, 2013, there is no panel. If I showed you the 2016 image alone, you don't know. But in the context of all these images together, you know. So the way to deal with that is just to, here's just the original Deep Solar. I'm just gonna click through. The methods are a little less interesting. But the way to deal with this is really to use what's called a CME's network. So, you know, neural network, you can inform that you have multiple images. One is your reference image, the other is a comparison that you want to do to the reference. And then you run this pairwise comparison, always with respect to the reference as 2017. And it works. And you can do this research, you get all of this data, so you will get something like this. In 2022, like last year, we updated this database all the way to 2022, so we have 3 million systems. That's about 20% more than Tracking the Sun was able to have last year. And it allows us to have a very deep look at where solar is nationwide and some conclusions that we were able to do. And this is the really cool part for me. Okay, great, you have all this data. Now what? What can I do with it? Well, one thing is you can look at different places and see the adoption happening, and you will realize, look at Los Angeles, it's happening faster than Suffolk County. Why did I pick these two places? The socioeconomics is very similar. So now here's an insight. I have two locations where the socioeconomics are very similar. Adoption started a little later in one of them. Obviously, the incentives are a little different. Maybe I can tease out which incentive is driving adoption. Okay, so econometrics can be used here, and we actually did that, and it does help you see that. The second thing that we realized was up to that point in time, a lot of the research said the adoption of solar PV is a linear phenomenon as a function of, you know, when you start, as a function of time, it's all going to be linear. And then the rate at which the adoption will happen depends on the income level. But we know there were some papers and some people saying, no, but look at all of the technology adoption follows the BAS model, where you have, you know, this is called the onset of adoption, 2008. This is when you have your ramp up. This is the ramp down time, and this is saturation. And then our question was, well, is this happening in solar? Before, people were not able to see it because they didn't have all of this granular data timed and labeled. And then we were able to do it. And not only that, we were able to actually find the drivers of this BAS model. So I'm going to skip that. So what are we able to do? We are even able to do things like this. Look at the fraction of groups that have not adopted solar, and look at the difference between low-income communities and high-income communities. It's quite a significant gap. We call that the solar adoption gap, the percentage or the rate at which high-income communities adopt more solar per household, number of homes in that area than the other. You can look at the saturation levels, and you can see that low-income communities reach saturation earlier than high-income communities. And so then we were able to understand by doing correlations of the parameters of the BAS model to various incentives that the big issue was your traditional rebate incentives, which were designed to encourage low-income people to adopt solar, were actually just working the opposite way and encouraging high-income people to adopt it. The reason being, the tax rebate, you need to have a good income so that you have a good tax, and then I can make sense of the rebate. And second, you needed to pay your solar systems up front. And poor people don't have credit scores that enable them to do that. I'm an engineer, and I kind of ventured into this with some colleagues in social sciences. And what I found is, wow, the economics is so important. No matter how much development I do in solar panel technology, the outcomes are going to be very dependent on the economics. And with this, we were able to actually show that performance-based incentives, which are simply an incentive that is paid every year for the number of kilowatt hours you produce, actually worked much better for low-income communities. Because somebody else could lease the panel for you, and then you directly get the incentive, and it all kind of worked out very well. So we also were able to do things like causation. So here's a little bit of the story about causation. Causality means if I correlate, outcome Y into factor X, it doesn't necessarily mean that X caused Y. And economists are particularly extremely obsessed with causation. And they have created methods that allow you to do what's called causal inference. But these methods, in my opinion, they're somewhat limited also because they require a ton of assumptions. But since we had so much data across the whole United States, we could actually run their causal inference methods while meeting all the requirements, because we know for each county level or census tract level, I can match two census tracts that are identical in maybe 100 or 50 socioeconomic parameters. And then the only difference might be one particular incentive was offered in one and not in the other. And therefore, I can tease out exactly how much did that incentive cause adoption. And so we are able to do things like that. And what we found, which is not surprising, but it's surprising that it's causal, is that the median income household, of the household, really has a huge effect on adoption, accounting for a lot of different things, demographics, solar radiation, electricity rate, etc. And you can see here, it's kind of exponential, right? So the intervention effect, the difference between the treatment and control is much smaller. So the last thing I wanted to talk about in solar was we took this data and we measured the difference in number of buildings with solar PV per census tract in non-residential and residential, accounting for whether you're a disadvantaged community or non-disadvantaged community. That's a classification of the US federal government. And we found, to our surprise, that residential solar is 63% difference. That's the gap. You want that to be 0% to be equitable, in our opinion. But non-residential commercial is only 35%. So we've said, really, microgrids should be deployed by these. For example, you have a large supermarket. They're going to put a solar system. Well, give them additional funds to put an even larger system and develop a microgrid and connect to the local community. That will result in a lot more equity than all the other incentive programs you're directly trying to do to have adoption happen. So this is just an example of our journey from using AI to detecting the solar panels and then collaborating with social scientists and economists to kind of derive all of these conclusions. And all of this work, had two sides to it. One, I learned through my research, I used to be just publishing in like very hardcore engineering journals and the AI conferences. And I noticed none of that was ever included in any real conversation at the government level, at the state level, by companies when they were making decisions about the grid. And I noticed, well, how do I do that? Well, we have to go to their community, and their community is nature, energy policy, etc. So we started publishing these works in those journals. Then we start getting invited into various town halls and things like that. And so it has been a very exciting journey for us from this technical side to actually some insights into this adoption and then seeing that being actually used by people. I want to go into show you, how much computer vision, again, can really help you and get some really clever results, to look at how to do adaptation to climate of distribution grids. So in order to do that, the first question is, I need to know where these distribution grids are. And I joined Stanford as an assistant professor in 2011. I got tenured in 2017. In all these years, every year, twice a year, regularly, religiously, I write to 7 of our utility partners who give us money to do research. And I say, can you give us this data? They said, no, we can give you more money, but we can't give you the data. That's not really available. That's safe. So we started looking into how to do this mapping. And initially, we worked a lot on what we call measurement-based mapping. So if I measure the power consumption of homes and buildings, and I also measure their voltages, so electric parameters, I can well, maybe not so surprisingly, actually reconstruct the power network, okay? You don't know, though, the topology physically. You know electrically how everything is connected, and roughly you know that every line follows streets, and you can roughly reconstruct everything, and we showed that that can be done using machine learning. But if we wanted the actual topology, exactly where things go, how do we use vision? That was the question we had. And we tried to do it with this overhead imagery, and we had seen some work from Meta or Facebook. They were using, you know, the overhead, but you can barely see the lines, and it was not performing very well, and their conclusion was this is not actually useful. And so again, we had an intern in the summer. We told him this problem. He started playing around, and you know, he found something amazing. This is for me really, really amazing, and shows you know how data is so pervasive. I didn't know this, but actually when you go on Street View, you can look up to the sky on your Google Street View. That's pretty amazing. You would never think that's true, right? Like, why would you have that? But the amazing thing is, if I look up in the sky, I see all the lines. And all you have to do is just trace those lines and piece them together using machine learning and computer vision. And I'm not going to enter into the details here. There's some methods, etc., and you're done. And then the more surprising thing is there is underground lines. So in the US, maybe 20% of the lines only are underground. Then what do you do about those? You can't see them. Well, what we found out is you take what you learned about the overground lines, apply a machine learning that predicts whether the certain street is part of the trajectory, and you do it that way. And the reconstruction is actually going to be very accurate. So, you know, let's make some assumptions. Buildings are connected to the nearby grid, etc. If not overhead and underground. Use the closest neighbor to connect all the dots. And here's kind of the performance of the method. We tested it in California. We also tested it in other countries. So deep solar has been tested in Germany as well and in Kenya. But here, California, Nairobi, so Kenya, Uganda, and Nigeria. And here's the precision. So in California, precision and recall, 85, 83%. Sub-Saharan Africa, without retraining, that's kind of the percentage. So surprisingly, a little bit higher on the precision, a little lower on the recall. But this is pretty impressive. And then you can do tricks and this and that and actually improve things to a higher level. But what we were interested in is this quantity called the undergrounding ratio. I take a zip code or the block you live, and I say, how many meters of electricity line are going through that? What percentage is underground? What percentage is overground? We know that line undergrounding is the only and the most safe protection against wildfires. It actually is the one proven method that dramatically reduces the risk of causing wildfires, and that also reduces the risk of being impacted by wildfires. So we took that quantity and we just did some basic socioeconomic plots, stratifying it by threat. So the state of California tells me for each zip code or census tract, what is the wildfire risk projected for that area for the next 10 years? So our fire organization is forced to publish that. We divided that number into 3 levels, low, medium, and high. And then we wanted to look at what is the fraction of lines underground as a function of the income of each location. And so, for example, what do I expect? One, if things are equitable, dependency to income shouldn't be there. And second, I would love to see higher wildfire threat areas to have higher percentages of line undergrounding. And what we see here is nothing of that sort. First of all, you can see that the undergrounding percentage ratios actually grow with income. So wealthier neighborhoods have a lot more lines underground. And not only that, look at wildfire threat high, the red line. If you're low income, you're actually way worse than wildfire threat low, even at low income. And so it's completely inequitable. And we found, that undergrounding does not really come into the communities that need the most, and that lower income communities have received less undergrounding. The same thing can be done for detecting wood pools, whether they're metal or wood, and then doing this plot. And now, so what do you do with this? We did two things. One, we proposed to the utility that you calculate this on a dashboard, and as you do projects, you take this into account. The reason why this came out this way is not necessarily because utilities are evil. They are just some economic agent, whether you believe that is evil or not. Now, why did they do that? Because the mechanism for undergrounding lines was that the community has to go and request that. And typically, wealthier communities have a community association, and they can go and request, well, the lines are not very nice and they're risky, can you bury them? And then there's two ways to pay for that. One is that you rate base it, means all ratepayers in the whole of the region of that utility will pay for that over a period of 30 years. So you get a small increase on your electricity bill. Or you can do local. So just that local community pays for it, which in some of the wealthier communities, they were willing to do that as well. So what we proposed is, well, one, start to publish and show these inequities and keep that as part of your decision making. And the second thing is, when you go doing undergrounding, we developed a method to do that using the fact that you can allocate the cost locally or rate-based globally. And basically, if you're in a poor community, you want it to be globally allocated. If you're in a rich community, locally allocated. And the difference we determined to be 100K. That is our cost allocation. And what we also have is an algorithm that went through all the lines and the risks and determined the 10 or 20% of lines that need to be buried. Of course, we published this research. The utility of this region is called PG&E, which went nearly bankrupt because of wildfires. Is a huge company, and it was nearly bankrupt. Their mechanism for doing this does not account for any of this. And they raised our electricity rates by 30% to pay for undergrounding, and they're only going to do 10,000 miles. And as far as we determined, maybe only 5% of the critical areas. Their algorithm had some weird considerations. So I think what is missing is that in this conversation, particularly adaptation, climate adaptation is huge, but adaptation is not an economical thing. You can't have a startup that does adaptation. It has to involve the city, regulatory agencies, utilities, if you're looking at electricity or water. Really what's missing is openness, open data, open methods, and open analysis, and community awareness of this so that we pressure people to do the right thing. Right now, the analysis that we looked at were all done by consultants. We don't know what assumptions were done, and we couldn't really figure out why they were doing things in a certain way. But of course, nobody will say that's completely wrong because utilities are serious companies, but lack of transparency, huge issue. AI can really cure that because it can bring the data to be transparent. And then people in a university or student groups can make this analysis and send them to the city hall. Like a lot of our work has gone into communities that now do the advocacy to kind of change these things. And we are very, very happy that people use what we do. We're not even aware sometimes. You see in the newspaper later on, but just to say, in this journey of AI, this was one of the few places I thought, oh my God, we can do something from the university and directly, immediately impact the world. Okay, so what is next? What are we doing next in this story of decarbonization, adaptation, and locating infrastructure? So we called it infrastructure informatics. That was my students' idea. One is really kind of raising the stakes, basically adaptively extract information from all sorts of remote sensing, not just these two initial sources we used. And then, you have like daily updates for different satellites. There's all kinds of like practical engineering considerations, lots of interesting machine learning problems. And then the other thing is you have text information that you can start correlating with that. We start our journey in that through, this is just showing you some of that, through this method called SkyScript that basically allows you to quickly do inference by just following text. I don't need to train the classifier each time and so on. The other thing we started looking at, and I'm going to skip that, is on resiliency. And here we have built the largest data set for the US currently available of the reliability of electricity for each county, community, etc. We used non-AI methods for that. We actually wrote to utilities. We took federal government data. We added a lot of utility data sets that by Information Act, I have the right to access, so you can go and write to them. And we combined that with a new set of climate indicators that we developed with some climate scientists that basically allow you to look at any location and take all of our IPCC data, that's the climate panel data, and transform it into something like cooling degree days, CDD. That means, okay, how many degrees above, 72 degrees am I on the summer? So the higher I am, the more hot is that summer. The lower I am, the less hot is the summer. You can create indicators like that for all of the weather events and then use it to analyze events at community level and so on. We're publishing all of that, and you could actually calculate it for one of the uses. I calculated for Brazil, and people who are making infrastructure investments are now thinking, oh, maybe I should take into account the fact that it's going to be super hot in this particular region, and therefore the grid, may not be able to transmit as much power, or my solar does not produce as much power. There's about a 5% variation due to climate. We were also able to do things like this. The reliability in a location, that's the y-axis here. How many minutes? The yearly SAIDI is the number of minutes without power for a given community, and the undergrounding rate. So we have a predictive model that we learned that is able to build this. And if you look at Miami-Dade, you can see right here is where they have their undergrounding today. If they did just a little bit more, it will really dramatically reduce their SAIDI. And the reason for this is Miami is on the path of hurricanes. Extreme wind is one of the biggest risks for power lines, and freezing rain. And that also we found in our research. We're able to do models like this, projecting the reliability to climate, and even things like which households can actually back themselves up using storage and solar in an economic way. Because there's this issue, everything is expensive, can I be economic? So we found like 60% of US households can actually do that, which is pretty amazing, because if they did it, it will upend the energy system as we know. And the only reason they are not actually able to do it in practice today is because the battery storage units are not available in that many units, and they don't have electricians, and they don't have people who can go and approve these project permits. So if you're an electrical engineer, you can go and learn to be an electrician, and you will make a crazy amount of money right now in the US, much more than the electrical engineer, because that's what we are lacking. Or you can work in the city and start thinking about quickly approving all these projects. So just as a summary here, and then we can jump into questions. We looked at the solar PV adoption, the distribution grid adaptation, and really the next generation of informatics for me is really resilience and adaptation with massive data, looking at various other types of images, combining with, of course, now the fashionable thing is LLMs, etc. But what's most exciting for me is once you generate this information using AI, finding actual value that you can take actionable decisions. So think about AI not as some sort of clever gizmo, but really, how do I create decision support tools for people right now that are saddled with a lot of information? They have to make a lot of choices. Maybe in the future, all of that will be taken care of AI, and we will be totally useless and receive some money from the AI to, enjoy the beach in Rio. That's where I'm from. I would love that, actually. But looking a little bit more forward, again, think about also all the actors. This was another change in our group over the years. We moved from, we are technology people and electrical engineer, and look at those people, don't even know how to model anything, to actively engaging government agencies, residents. We organize events for communities. We bring a lot of the policymakers or even people in the regulatory agencies to Stanford and train them in some of these things. And I really, really believe that here's where there is a lot of opportunity for research, which is AI and data science is developing, but there needs to be domain knowledge that you can inject. In our analysis here, in a lot of it, it's not just pure machine learning. We injected the domain knowledge in the correct way, and that can be tremendously valuable. And the last piece is in the journey in Stanford, and I wanted to share this as just as a small anecdote, not as like something to be proud of, but it's very important to also figure out some things you want to make it free so people can use. Some things you want to use it to train other people and bring it closer to you. Some things you may be inspired by and then think of there is an actual economic opportunity. And to do economic things like a startup, the most important thing is finding the right people. Technology is a solvable issue. Never a technology resulted in a great startup. At least I talked to a lot of startup founders that are extremely successful at Stanford. And typically what they found is it's really about the people you work with and picking a good problem. And then you figure out the answer. So in Stanford, we decided to put this to test, and we developed this startup with Amit is a former founder of a very successful startup in energy called AutoGrid. And of course, myself and Arun are faculty at Stanford. Arun is the dean of the School of Sustainability, and Liang directs my program for the grid. And we just decided to try to go and understand, in this area, if we have better information, where can we actually help the grid? And there's some commercial opportunity. Well, right now, it's in this area of interconnections to the grid. If I have a data center or I have a new generation project, right now, my interconnection approval time is 3 years. You have to go into queues to determine whether you can be interconnected. The queues closed down this year because 80% of the projects were being rejected. Can you imagine how you're going to decarbonize the economy if we can't connect anything into the grid? It's totally impossible. Not to talk about transmission upgrades and all of that stuff. So what we found is a lot of process issues that you can improve, a lot of issues around simulations that can be done better, and that's kind of what we are doing in this startup. But I do believe this is like just scratching the surface. This whole triangle I showed you in the beginning, just on the grid, what we hear talking to a lot of people with a lot of industry history in this area, this is almost like rebuilding the grid from scratch, which is like a $1 trillion opportunity globally. So it's huge, much bigger than even the web was. The only difference is the web, you can do it without any regulators and real people just can be some guy. I used to love programming or girl and go into a room, program, and do whatever you want. If the website is crashing and people are complaining, you can just give you a screw you and do the next thing. Nobody's going to accept that for the grid. So there's a little interesting thing of how do you take AI, information technology, and bring it to that. So thank you. Opening for questions. I ran over by 5 minutes to what I promised Marek.
Thank you so much, Professor Rajagopal. It's not every day that you can hear a Stanford lecture in the middle of Prague at CTU, but here we are. In fact, I did some quick math, and during a standard Stanford term, you would get right about 24 of these lectures. And given that the average tuition at Stanford is $60,000, this lecture would be about $2,500 US or 56,000 crowns. So you're welcome. We'll be collecting some of that. And, just kidding. But we have time for about 1 or 2 quick questions, if there are any. I would say for 2,000 crowns, would that be? No. Good. All right, go for it.
So you have mentioned that one of the goals of this project is to increase the resilience of the entire grid. But so far you've only mentioned like natural disasters. But what about the adversarial attacks? Something like, let's say some rogue organization tries to disrupt the power supply. So are there any areas in which AI can help against that?
It's a great question. I'm not an expert on security. I work with a colleague, Phil Levis, who is much more into that, and he collaborates with another super famous faculty. The name is escaping me, from Stanford CS, computer science, on that. And yes, there is some research that can be done, but what they found when we introduce the industry folks that we bring through our program to them is that, shockingly, they're so behind on following kind of the standards, what you have to do in terms of existing practice, that research seemed a little bit like, well, I can't do research if you can't even bring your systems to be done right. So there's a huge economic opportunity, which is helping these grid operators in handling this distributed energy resources in particular, which is a new form of energy resource. It connects and communicates via the internet, which is not the case for the larger equipment and stuff like that. It has their own dedicated communication lines. And so, and then on the physical side, where you can actually damage and attack physical infrastructure, there is a lot of good research that has been done on that. So definitely it is an interesting area. Our research did not address that, but right now I am working on a project with the US Navy, and they asked us if we can help with the resiliency of the Navy base. And I said, what is resiliency? Well, we need to power through a outage. And in the US and California, you can think 1 day to 3 days, maximum 3 days. It was the worst of wildfire season we ever had. It was like 3 days without power. They said, no, we want 1 month. And I said, why? Well, we already know that malicious actors, certain countries, and you can imagine what they are, actually have the ability to turn off the US grid for 1 month. They have that ability right now. And if we go into some real war, that's I guess the implication is if you go to real war, then they will turn off the grid for a month. So then you have to start thinking about renewables and local generation, storage, and really a physical architecture of the power provision. What's the cost of that? So that's also, it's not so much answering your question of detecting the attacks, but the addressing it.
In general, reducing the potential impact one
Yeah.
actor can cause.
Yeah, there is later on, if you email Marek, I can connect you to some of the researchers at Stanford, but also I have some colleagues in other places who look at this. But what I've not seen, to be honest, is, they are all into like this electrical engineering, computer science papers, very, very technical, but raising that to understanding what can a regulatory agency or people actually doing investments in the grid, how can they use that information. Oh, the capability of detecting is important, and this is the advantage. It reduces the downtime of the grid by so many percent, and those kind of studies I've not seen also. So that's another huge gap, an opportunity to publish.
Awesome. Thank you very much. Is there one more question? All right, go for it.
Thank you so much for the presentation. It was very interesting. I really like how you sort of came up with different proposals of like, that decision variable at 100K income. And it seems like that could be incorporated into policies, maybe on the California level or even a federal level. I'm curious, do you have avenues to actually get the real decision makers to look at this and pay attention to it?
Yeah, right now I have one of my students is spending time at the California Energy Commission and implementing some of their research as part of their, because they have no idea actually makes it all the way to a level of policy. They have analysts inside these agencies and you really want to connect to them and talk to them about the modeling and how they can incorporate it and compare various proposals. They have a list of proposals they have to evaluate economically, and then you can add yours into that list. That's based on advocacy. So somebody advocates for that thing and is also economically feasible. So there's two assessments that need to be made independently. The advocacy can happen from inside an agency or from communities. For example, for distributed energy, it's really a community decision that wants to adopt it. They can push, state-level organizations in the U.S. to provide some incentives for that. And that's starting to happen. But I think there's a lot of opportunities even outside of this policy world, just thinking about, for example, making slight changes, so maybe it's still policy, but making some changes. I was talking to a colleague and he was saying, if your distributed storage, if you could show that actually it provides a certain amount of buffering for a certain number of hours, that I can disconnect your house from the grid and etc., it should have a value for the wildfire protection. That money should be given to you as an incentive for the storage. And actually utilities are very keen on that because they don't want to have to bury all the lines. It's a lot of work and the maintenance is really difficult. So there's a lot of opportunities like that as well. So I don't know exactly how the energy environment works here in the Czech Republic, but obviously, Marek's group has a lot of faculty looking into this, and you can take some ideas like this and very quickly start thinking about, well, what would make sense to do here? This is the other cool thing. Unlike, you can't have a Google of this, one company that solves the same thing to everyone. It's going to be very local. And it's going to be about small, medium-sized companies, consultants, etc., doing their job. So it's a huge opportunity for people who want to become independent and even wealthy to some extent.
Thank you. Okay. Thank you once again, Professor Rajagopal.
Thanks.